Hello. Today we're going to be starting our section on permutations and combinations, but we're really going to be focusing on those permutations today. We'll get into combinations a little more on Friday. So our goal is to be able to find permutations and combinations. So we're going to be looking at problems that ask things like, in how many different ways could you choose a sandwich, side dish, and dessert if we have a menu like this cafeteria menu? So our whole goal is that we can understand to use different counting methods to find the number of possible ways to choose objects with and without taking into account order. So if we look at this first tree diagram, and we are packing for a weekend trip, and we have 3 different pairs of pants. Pant 1, pant 2, pant 3. What you can do is make a tree diagram here and pair each pair of pants with shirt 1 or shirt 2. So you could wear your first pair of pants with your first shirt or the second shirt. You could wear your second pair of pants with your first shirt or your second shirt. And you could wear your third pair of pants with your first or your second shirt. So if we're looking off here, my handwriting is not very good, so you're going to have to bear with me. We can see that we have 1, 2, 3, 4, 5, and 6 outcomes. So there's 6 different choices that we can come up with if we have 3 pants and 2 shirts. The reason that we got 6 was we just multiplied those together. So if we ever had, instead of just 3 pants and 6 shirts, if you pack like me, and you have about 10 pairs of pants and at least 12 shirts, plus 8 different pairs of shoes for a weekend trip, you can really save some time by not doing a tree diagram and by using what we call the fundamental counting principle. So for this next one, we have a pizza shop, and they offer 8 vegetable toppings and 6 meat toppings. If we want to solve the problem, how many different pizzas can we order with 1 meat topping and 1 vegetable topping? What we could do here is we could do 8 of the vegetable toppings times 6 of those meat toppings, and we could create 48 different combinations with 1 meat and 1 vegetable. So for the next one here, we have one type of Maryland license plates that had 2 letters followed by 4 digits, 4 numbers. How many of this type of license plate were possible? So what I do for these problems is I just create a blank. You have 2 letters followed by 1, 2, 3, 4 numbers. So in each of those blanks, we're going to fill out how many different options we had. Well, for this one, if we think how many letters are in the alphabet, we would have 26 different options for 2 letters, and it doesn't say anything about not being able to repeat those letters. So we're going to assume that we can have the same letter again, like A and then an A, but we have 26 options again for the second letter. As far as digits go, we could have 1, 2, 3, 4, 5, 6, 7, 8, 9, or 0. So actually there's 10 different digits that we can choose from. 10 different digits for the second number, 10 digits for the third number, and 10 digits for that fourth number. So what we can do between them here is use that fundamental counting principle and multiply all of these together. And if you guys are following along, you should see that we're going to get 6,760,000 different combinations for how many license plates possible. That's crazy. Just 6 blanks there, 2 letters and 4 numbers. Okay, so this leads us to, let's think of your cell phone code. So if you guys are like me, you have an iPhone, possibly, and you've locked your iPhone with, I chose a 4-digit code. You could also do a 6-digit code, and then we'd have even more possibilities. So for our cell phone code here, we only have number options, as far as I know. So we're going to have 1, 2, 3, 4 different numbers that we could type in. And we know we have 0 through 9. So again, we have 10 options for the first number, 10 for the second, 10 for the third, and 10 for the fourth. So again, we're multiplying 10 times 10 times 10 times 10 to find out how many possible options we have for our phone combination. And when we multiply all those together, we get 10,000 different combinations, and that's with 4 digits. If we wanted to find out with 6 digits, we just multiply by 10 again, and one more time, so we'd have 6 tens multiplied together. All right, let's go ahead and move forward here. So if we have a problem where you can't reuse the same number again, so let's say we have a batting order. We have 9 players. There are 9 choices for the first batter. So we could pick anybody, oopsies, we could pick anybody to bat first, right here. So we have 9 different players to choose from. But once we've picked that first person to bat, there's only 8 people left to choose from to bat. So we have times 8 for the second choice. Times, now we've picked the first 2 batters, so there's only 7 left for the third choice. 6 batters left for the fourth, 5 for the fifth, 4 for the sixth, 3 for the seventh, 2 for the eighth, and 1 for that 9th place batter, the 9th batter in line here. So what we're doing is we're multiplying 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and we get 362,880 batters. Or sorry, 880 different combinations for picking the order for 9 batters. Okay, and we can definitely type that into our calculator. And there's also a shorthand way to write this. So instead of having to write out 9 times 8 times 7 times 6 times 5, we have a symbol that we use. We write 9, the number that we start with, and when you're multiplying all the way down to 1, we use what looks like an exclamation point. It's called a factorial. So this is read 9 factorial, and that's a shorthand way to write 9 times 8 times 7 times 6, 5, 4, 3, 2, and all the way down to 1. Okay, so if we are looking at how many different ways we can rearrange, let's say, the letters in the word car, C-A-R, we could write this out. We could do, actually I'm going to type this. We could have C-A-R, we could have C-R-A, we could have A-R-C, A-C-R, those are all different. We could start with R, do R-C-A, we could do R-A-C. Did I leave any out? No, I think that's it. So we have 1, 2, 3, 4, 5, 6 different ways to rearrange those letters. We could do the same thing for the word boat. But now, since we have 4 letters instead of just 3, this is going to get a bit more complicated. We're going to have to spend some more time trying to rearrange them. B-O-A-T, B-O-T-A, B-A-O-T, B-A-T-O, and so on. We could keep going. So you're probably thinking there's got to be a shorter way, and you're right. So here we have 3 letters that we're trying to rearrange, and we got 6. And so all we're doing is taking 3 factorial, which is 3 times 2 times 1. My pen's not working here, which gives me 6. So again, that's 3 factorial, which is 3 times 2 times 1 which gives me 6 different options. We could do the same thing here for the word boat. We'd have 4 factorial, which is 4 times 3 times 2 times 1, which is 24 different combinations that would take significantly longer than trying to find only 6. So now that we've talked about factorials and we know what that symbol means, it looks like an exclamation point, this allows us to get into something called a permutation. It's just an arrangement of objects in a different order, specific order. So for permutation, the main thing here is order. The order that you have those objects in really, really matters. It makes a difference. So for example, if we have 5 books to be arranged on a bookshelf, how many different ways can we arrange all 5 of those books? So this is exactly like that problem that we just did that we used factorials. So this would be like saying we have 5 options for the first book, 4 for the second, 3 for the third, 2 for the fourth, and 1 for that 5th book. So here, when we type all that in, we get 120 different ways to rearrange the books on that shelf. There's another way to think about that, though. If we have a factorial, like 5 factorial, which is what we just did, we can also think of that as a permutation. And so what that is we have 5 books, and it looks something like that. Okay, I just rewrote that. So you have 5 objects. This is how many objects that you have, and you're arranging them 5 at a time. So when we solve for a permutation, 5, and we're arranging 5 at a time, we have a certain equation that we use for that, and we're going to get to that next. And here is that lovely equation for permutation. So if you have your notebooks out, go ahead and write this down. If you don't, get your notebooks out and write it down. So we have the expression NPR represents the number of permutations of n objects arranged r at a time. So n, this first number, is always going to be either bigger or the same size as r. You'll never have n smaller than r. You can't have, for example, here we have 8, and we're arranging 2 at a time. We could never have 2 things and arrange 8 at a time. There wouldn't be enough to pick from. So this NPR equals n factorial over n minus r, that whole quantity after you've subtracted, factorial. Okay, so if we're trying this, we have a permutation of 4 objects arranged 2 at a time. So this is going to look like 4 factorial divided by 4 minus 2 factorial. Okay, and then we just simplify each step at a time, and there's a couple things that you can do to kind of make this a little easier on yourself. So 4 minus 2 is just 2 factorial. So if we write that out, 4 factorial is 4 times 3 times 2 times 1 divided by 2 factorial is just 2 times 1. So what happens here, you can see that there's a 2 divided by 2, 1 divided by 1. Those two cancel out. So this whole thing is just 4 times 3, which is 12. And that would be your final answer for how many different ways you can arrange 2 objects from a group of 4. And the order matters. Okay, for this next one, we have 6 objects, and we're arranging 4 at a time. So this might be something like you have 6 students in class, and you're awarding the first 4 medals. How many different ways can you have those 6 students be ranked first, second, third, and fourth? That would be an example of a permutation where that order really, really matters. So here I have 6 factorial. That's the number of objects here that we're choosing from. This is like your n from your equation right there. This is like your r from your equation right here. So that's 6 factorial divided by 6 minus 4 6 minus 4 factorial. So when I simplify that, I have 6 factorial over 2 factorial, because 6 minus 4 is 2, and the factorial is still there. Okay, so I'm going to have 6 times 5 times 4 times 3 times 2 times 1 in the numerator, and 2 times 1 in the denominator. So I can see that parts of this will cancel out when we divide, the 2, of course, and the 1. And then I just have 6 times 5 times 4 times 3. Okay, so I'm just multiplying all of those numbers together, and when I do that, I get 72. Ooh, so that's a 2. 72 different ways to order 6 objects if we're arranging 4 at a time. Okay, so at this time, I want you to have your sub or whoever hit pause on the recording, and I want you to do 8 and 9 on your own. Okay, so hit pause, and I'll come back with the answer. All right, time to check your work. For the first one, we have 10 factorial. That's how many objects you're choosing from. And we're arranging 2 at a time. So it's 10 factorial over 10 minus 2 factorial. When we type all that in, we get 90 different ways to arrange those objects. And for this one, we have 5 objects arranged 4 at a time. So this is 5 arranged 4 at a time for your permutation, and you get 120. So hopefully you got 90 for 8 and 120 for 9. Okay, the next one. We have 60 songs on our music player. In how many different ways can you arrange 5 songs to listen to while exercising? Okay, so when I'm going to write this, I'm creating this myself. So I have 60 songs total. This is a permutation. The order that you play those songs matters for this one. A different order is a totally different playlist. So we have 60, and we're arranging 5 of those at a time. So to set this up, we're going to have 60 factorial over 60 minus 5 factorial. And I want you to type that in your calculator with me. And there's a shortcut for this, and I can walk you through it. However, if you get lost, you might just want to Google how to type in factorial in your calculator. So what you're going to do is you're going to type in your 60. And then you're going to go to the button that says PRB. So I'm going to walk you through that shortcut on your graphing calculator. I don't know how this is going to work, but I found a video. If it doesn't work out, I'll make sure I attach it and email it to you. So here we go. She's going to walk you through how to do that, and I'll kind of narrate over top of what she's saying. She's going to find 9 factorial. So on your calculator. So she typed in 9 already. Now she's going to this probability button, PRB. So go ahead and do that on your calculator. There it is, the factorial button. So you need to scroll over to it, arrow over to the right. Okay, then hit enter. Now you have 9 factorial on your calculator. Hit enter again, and you get what that factorial is. So for us to do that, we're going to go back to 60 factorial. I want you to do this in your calculator, okay? So let's go type in 60, hit that PRB button, arrow to the right twice to where there's a factorial, hit enter. And then what you can do is in your calculator, you don't have to write that huge number down. You hit your division button. And just like you see it on your screen here, you're going to type that in parentheses, or we know 60 minus 5 is 55. So you're going to do 55 and back to the PRB button to hit the factorial again. And we can see what that number is on our screen, okay? So once you've typed that in, you should have the following number. And I'm going to type it because it's very long here. Maybe not. I'll write it, but it's going to be sloppy. Okay, that's what you should see on your calculator. 655,381,440. All right, now go ahead and practice permutations in your assignment, and we'll do combinations tomorrow. Bye.